one more theorem on the greatest common divisor. So what is the theorem? Any two non-zero integers a and b have unique greatest common divisor, and that is denoted by suppose d in round bracket a comma b. That is the notation for greatest common divisor, and can be expressed in the form d is equal to, or greatest common divisor of a and b is equal to ma plus nb for some and m and n belongs to z. Already the examples of these theorem application of these theorems are already observed in the previous lecture, that this types of example, that find greatest common divisor of these two numbers, and this answer, that is the greatest common divisor of these two numbers, is unique. The answer of all students are same. So the greatest common divisor of any two non-zero integers is unique, is only one. Answer is only one. Okay, and this is the first part of this theorem, and we have to express it in the form, or we observe that it express, that is the greatest common divisor d of these two numbers expressed in this form, that 3997, that is a into m plus b into n for some m and n belongs to z, or use the letters x and y instead of this m and n. So already applications of these theorems are observed in the previous lectures. So that is the greatest common divisor of two integers, non-zero integers, is unique. Answer is only one, and that greatest common divisor expressed in this form for some m and n belongs to z. Now we have to prove this theorem in two parts. Now first we will show that d is the greatest common divisor of these a and b, and is unique. Okay, so we know the definition of greatest common divisor, that a and b are any two non-zero integers. Then that in another integer d is said to be greatest common divisor of this a and b if d divides to both, d divides to a as well as d divides to b, and if there is another common divisor of a and b, suppose c divides to a and c divides to b, then c divides to d. If these two conditions are satisfied by d, then d becomes a greatest common divisor of a and b. So we define the set S as ax plus by for some x and y belongs to z, and ax plus by is strictly greater than 0. That is ax plus by, a is integer, b is integer, x is integer, y is integer. Here is the x and y are integers, a and b are integers, and therefore x and by both are integers, because multiplication of integer is integer, and therefore, and the addition of two integer is integer, therefore ax plus by is integer, means is the element of z, and it is greater than 0. Here is the condition that ax plus by is greater than 0, means this S is subset of what? Natural numbers. That is, this set contains the elements 1, 2, 3, 4, 5, 6 up to infinity. Out of these elements of natural numbers, some are exist in S. Means S is subset of natural numbers, set of n, capital N. That is set of natural numbers. We will show that this S is non-empty. That is, this S contains at least one element. When S is non-empty set, if the set contains at least one element. Now we have to show the one element belongs to S. So for that, this is the calculation, that suppose a and b are non-zero integers. Obviously, a and b are non-zero integers means they are positive or negative, but their squares are always positive, because the square of positive is positive, also the square of negative integer is integer. So a square plus b square, this number is both are positive, therefore their addition is greater than 0, strictly greater than 0. Okay, and a square plus b square is of this form, a into a plus b into b. Suppose this a is suppose x, and this b suppose y, then this element is of the form ax plus by. This a square plus b square is of the form a square b square is of the form ax plus by, for x is a and y is b, and this number is greater than 0. Also this number is greater than 0. That is this condition, and therefore a square plus b square belongs to S, is the element of S, because it is of the form ax plus by, and it is and ax plus by is greater than 0. That number is greater than 0. A square plus b square is of the form ax plus by, and a square plus b square is greater than 0, strictly greater than 0, and therefore this a square plus b square satisfies the all properties of the set S, and therefore this a square plus b square belongs to S, present in S, and therefore we have one element in S, and therefore S is non-empty subset of N. Obviously, this is by using definition of S, we can say that S is a subset of N, and here we have shown that a square plus b square belongs to S, therefore S is non-empty, and therefore the common sentence, aggregate sentence is what? S is non-empty subset of N. Okay, and therefore by well ordering principle, what is well ordering principle? Every non-empty subset of N has least element, and therefore by well ordering principle, as because S is non-empty subset of N, and therefore S has least element, and suppose that least element is D, say D, that is D is the least element, means D is the element of S, and D is less than or equal to Z for all Z belongs to S. That is, D is the smallest element in S. That is, all the element of S, remaining elements of S are either greater than or equal to D. Okay, and that because D is the least element, therefore D is what? Less than or equal to Z. Here use any notation Z for either use a Z or W or any notation for all Z belongs to S. That is, D is least element in S, the set S. That is, D is smallest element of S, least element of S. And why this least element exists? Because of well ordering principle. What is well ordering principle? That every subset of, this is the well ordering principle, every subset of this is well ordered, every non-empty subset S of non-zero non-negative integers means uh, set of natural numbers, okay, contains a least element. So by using this well ordering principle, as S is non-empty subset of N, and therefore S has a least element, that is, we have the least element in that set, and let it be D, small d, and therefore D, as the D is the element of S, therefore D is of this form ma plus nb, because every element of the S is of the form ax plus by for some x and y belongs to. So instead of x and y here, use m and n. And so D expressed in the form ma plus nb for some m and n belongs to. Because this is the property of the set S. Once the element belongs to S, it is of the form ax plus by for some x and y belongs to Z. So here, suppose m and n exists such that D is equal to ma plus nb for some m and n belongs, because S is, D is the element of S, and every element of S is of this form, that a into some integer plus b into some integer. So take that integers as m and n or any another notations. And so this is proof that D expressed in the form, D is greatest common divisor, and D expressed in the form, not the only what is proof up to this, that D expressed in the form ma plus nb for some m and n belongs to Z. Now we have to show D is the greatest common divisor. Then we can say that the greatest common divisor of D expressed in the form ma plus nb, and then we show this D is unique. This D is unique is the next part. So now we will show that D is the greatest common divisor of A and B. In the first part up to this, what we show that D expressed in the form ma plus nb by taking this set S. And now we will show that, now we prove that D is the greatest common divisor of A and B. So for that, first show that the D is a common divisor of A and B. That is the first property of greatest common divisor. We will show that D is a greatest common divisor of A and B. So when D is a greatest common divisor of A and B, first D is a common divisor of A and B, and the next condition. So now we will show that D is a common divisor of A and B, and then applying the division algorithm to A and D, because A and D are two integers. So and so divide A by suppose D. We have some question, we have some remainder. So there exist, applying division algorithm to A and D, there exist integers Q and R such that in Z, such that say that A is equal to, that is, if you divide A by D, then suppose Q is the quotient and R is the remainder, where obviously this remainder is strictly less than divisor, that is D, and greater than or equal to 0. This is by using division algorithm. And as if R is not equal to 0, this second gives R A minus dq. Suppose R is not equal to 0, and then what we have, R is equal to A minus dq, with R strictly less than D, greater than equal to 0. And then what is D? D is ma plus nb from this equation, that is, substitute that, and then take this A as common from these two factors and B here. Then what we have here is 1 minus mq into A minus nq in bracket minus nq B plus into B plus minus nq into B, where R is strictly less than D and greater than 0. Okay, greater than or equal to 0, or just type greater than 0, because we here assume that suppose R is not equal to 0, therefore R is strictly greater than 0. Thus R is strictly greater than 0, and what is your observation here? Suppose this is x and this is y, then what, that 1 minus mq is x and 1 y minus mq as y, and then what we have, R expressed in the form ax plus by. Okay, and R is greater than 0 here from this, and therefore R satisfies this both property, that is, it is of the form ax plus by and it is greater than 0, and therefore R is the element of S. Here is the sentence, R is greater than 0 and is of the form ax plus by, for x is equal to 1 minus mq, y is equal to minus mq, and hence R belongs to S, because it satisfies the two properties of the set S, that is, it is greater than 0, R is greater than 0, and is of the form ax plus by, and therefore R belongs to S. But this is contradiction to the choice of D, because D is the least element of S, means there is no element in S which is strictly less than D, because D is the least element. All the element of S are either greater than or equal to D. No element in S is strictly less than this D. But here we have the element R which is strictly less than D. Here is the R strictly less than D, and this is contradiction to the choice of B. This is not true, because D is the least element, and why this contradiction arise? Hence, and therefore R is not equal to 0 is a wrong assumption. That is, what is the true? R is equal to 0. That is, if R is equal to R is not equal to 0, then we have the contradiction, and therefore R is equal to 0. Okay, because if R is not equal to 0, we have the contradiction, and therefore R is equal to 0. We have the false statement, we have the wrong statement, that is, D is the least element. This is wrong, because R, and hence R is equal to 0, because R is least element, and it is not true that there exists an element in S which is strictly less than D, and hence R is equal to 0. This is wrong, means what is correct? R is equal to 0, and R is equal to 0 means A expressed in the form dq, and therefore this implies what? D divides to A. D divides, because A expressed in the form D into some integer, and therefore D divides to A. Similarly, we can show that D divides to B. Okay, as same procedure, no need to show it. It is that D divides to B. We can show right directly that similarly we can show D divides to B. Instead of this A and D, we apply division algorithm to B and D. We have this statement that B divides to D, not B divides to D divides to B. If we apply division algorithm to, instead of A and D, we apply division algorithm to B and D. So no need of writing that, write directly that similarly we can show that D divides to B. And thus the first condition is prove that D is a common divisor of A and B, that is, D divides to A as well as D divides to B, the first condition of the greatest common divisor. And now we have to show this, that is the second condition. What is the second condition? D is greatest among all common divisors. That is, if there is another element C divides to A and C divides to B, then C divides to D. We have to show this. This condition indicates that D is greatest among all common divisors. And so suppose that there exists another number C such that C divides to both A and B. Suppose C be any common divisor of A and B. We assume that there exists a C such that C divides to A as well as C divides to B. Now we have to show that this D is a greatest common divisor among all common divisors. So for that, let's assume that C divides to A, C be any common divisor of A and B, means C divides to A and C divides to B. So C divides to A implies A expressed in the form C into some integer, and C divides to B means B expressed in the form C into some integer. That is, suppose K1 and K2 are two integers. Okay, because C divides to A and C divides to B. Our assumption is what? C divides to A and C divides to B. So C divides to A implies A is equal to CK1, and C divides to B implies B is equal to CK2 for K1 and K2 belongs to Z. And use this in equation 1. Use these values of A and B in this D is equal to M A plus N B. Substitute A and substitute B. What do we have? D is equal to M CK1 plus N CK2. And take this C as common. Then we have M K1 plus M K2. And this M K1 plus M K2 is the integer, because all M N and K1 K2 are integers, and multiplication and addition of integers is integer. Therefore, this number is integer, and therefore D expressed in the form C into some integer, and this implies C divides to D, and therefore this condition is satisfied that if C divides to A and C divides to B, then C divides to D. We have C divides to D, means D is a greatest among all common divisors. This condition indicates. So in the first condition, D becomes a common divisor of A and B, and here we show that D is the greatest among all common divisors, and therefore thus D is the greatest common divisor of A and B. And now it remains to show that only uniqueness of D, because in this theorem the statements is what? Any two non-zero integers A and B have a unique greatest common divisor A and B, and can be expressed in the form. So in this, up to this, the proof is what? D expressed in the form ma plus nb, and then next part is what? D is a greatest common divisor of A and B, and that's why what we have, that any two non-zero integers A and B have a greatest common divisor D and can be expressed in the form ma plus nb. Now it's only to show that D uniqueness of D, that is D is a unique. We assume there exist two greatest common divisors of A and B. Suppose D and D dash both are greatest common divisor of A and B. Suppose that D dash is another greatest common divisor of A and B. Now we have to show the uniqueness of this theorem, D. We assume that there are two greatest common divisors of A and D. So suppose D dash and D are the two greatest common divisors of B. And as D dash is greatest common divisor, it is common divisor of A and B. That is D dash divides to A as well as D dash divides to B. But D is the greatest common divisor, and that's why by using the second condition of the greatest common divisor. What is the second condition of the greatest common divisor? That is, if there is another common divisor of A and B, suppose C divides to A and C divides to B, then C divides to D. And as D is a greatest common divisor, since D is a greatest common divisor, and D dash divides to A and D dash divides to B, suppose this D dash means suppose C. That is, if C divides to A and C divides to B, then C divides to D by using the second condition of the greatest common divisor. And therefore D dash divides to D, and D dash divides to A, D dash divides to B. Why D dash is greatest common divisor of A and B? Means D dash is what? Is common divisor of A and B. And then D dash divides to D dash is common divisor, means D dash divides to A and D dash divides to B. And as a D is greatest common divisor, by using second condition, we have D dash divides to D. Similarly, D is a greatest common divisor of A and B, means D is a common divisor of A and B. And as D dash is also common divisor, greatest common divisor of A and B, and as D dash, as D divides to A and D divides to B, by using second condition, we have D divides to D dash. That is, in the first sentence, consider D as the greatest common divisor and D dash as common divisor. And in the second sentence, suppose that D dash is the greatest common divisor and D is a common divisor, and then we have D divides to D dash, and thus D divides to D dash and D dash divides to D means D dash and D are same or different in sign. D dash is equal to plus minus D, because when the two numbers divides to each other, if they are same, for example 4 divides to 4 and 4 divides to 4, or 4 divides to minus 4 and minus 4 divides to 4, that is if the numbers are same or different in sign only, then the numbers divides to each other. And so D divides to D dash and D dash divides to D implies D and D dash are same or different in sign, that is D dash is equal to plus minus D. But D and D dash are greatest common divisors, and the greatest common divisors of any two integers are always positive. Greatest common divisors are always positive numbers, and therefore there is no negative sign, means D is equal to D dash, or D dash is equal to D, means if there is another greatest, if we consider D dash as another greatest common divisor of A and B, then it is equal to D, means D is a unique. And here the proof of the theorem completed, that that any two integers, non-zero integers A and B have the same have a unique greatest common divisor, and it expressed in the form ma plus nb. Already the examples of examples on this theorem are observed in the form that find greatest common divisor of two integers and expressed in the form of ma plus nb.